Thanks. I'm Colin Slater, and I think I'm kicking off a series of talks about the Rubin Observatory. And I'm going to start by giving you kind of the high-level overview of the observatory, and particularly some of the data management aspects that I work on. Um, so the first, like the most exciting thing is to just be able to say that like after giving talks for so long, talking about Rubin as being a thing in the future that we will eventually get data from, is now an up and running functional observatory. Um, so uh, sorry. Uh, we're now actually able to talk about like what are we doing, what data are we collecting with the observatory. It's a wonderful change. Um, So to bring everyone up to speed on just like the overview of what Rubin is, this is a brand new observatory built on Cerro Patron next to Gemini and SOAR, 8-meter class mirror, and it's dedicated to doing a survey. Um, so the Sorry. So we have one instrument that's a sort of large single imager with about a 10 square degree field of view, sort of 6 standard filters. And the survey this is going to do is something that we call the legacy survey of space and time. And so we've planned out the sort of next 10 years of observations for this observatory. And that survey is designed around four main science themes. So it's one sort of integrated program that's designed to answer questions in all these different domains. So those science themes are dark energy and dark matter, finding objects in the solar system, exploring the transient optical sky, be it from explosive transients, be it from variable stars, be it microlensing, and then also mapping the Milky Way. So the key to getting high efficiency in a survey like this is using a large camera to observe as much of the sky in every single visit as possible. So LSSTCam is that's the camera that I'm showing you on the left here. We're looking in the optical barrel at the focal plane. So there's 189 sensors. Each of them are 4K by 4K pixels. So it adds up to about 3.2 gigapixels. Um, Up in the top right, you can see what the projected focal plane looks like on the sky relative to the full moon. It makes the moon look small there. Um, the survey is designed around sort of a nominal 30-second exposure length for every single visit. Um, and when you add up how much sky we can observe in 30 seconds in one night, that adds up to about 750 visits. And if we observe that over the course of um, over th sorry, so over the course of 3 nights, we'll observe about the entire what can be observed from at any given time. So we basically cover the entire observable sky every 3 nights. Um, The sort of nominal point source steps are listed here for both single visits. So we get to in the kind of 24th magnitude territory for GNR just from every single 30-second visit. And then once we start co-editing those visits, we get into the 26th magnitude territory after 10 years of observing with LSST. Um, so I won't go too much into the actual survey cadence and the footprint, but just to say that there's been a lot of work on optimizing what we're observing, but then once we've taken those observations, all of the images are processed by basically a common set of pipelines that's designed to extract all the measurements that are useful for all of the different science cases that we're trying to satisfy. Um, so we're not sort of sectioning off images into like this pipeline or those images into that pipeline. They're all being processed by basically a common set of tools and algorithms over the entire data set. So I'm going to go a little bit into what those data products look like. So we have kind of two key cadences on which we produce data that we then release to the users. So first, during the night, basically as soon as we can, which is going to be in the kind of 1 minute to 2 minute range after shutter close, we want to release to the users any information we have about anything that's changed in images. So we'll be doing difference imaging between the image we took and template images, identifying anything that changed, and we're going to package that up and send that as an alert to users as soon as we can. And I'll say a little bit more about that in a minute. The other timescale that is important here is the annual timescale. That's when we do our data releases where we do a much more comprehensive analysis of all the data we've taken. We get both information on static sky science and on time domain science. So talking more about those prompt products, um, all the real-time processing is really focused on getting image differencing to the users as soon as possible. So the sort of set of science use cases we think this meets are things where you need to either do follow-up observations or you need some sort of timely response to something that's happened. So if something is changed in the sky, you need to be able to follow it up and it right that night or that week or that month, it's not going to do you any good to have to wait for the data release, which might be a year away. So we want to release that information as soon as possible. When we do this image differencing, we both detect every single thing that has more than a 5 sigma change from the template image. These templates are typically from coads that we made in previous data releases. So we do that difference imaging, identify anything that's changed. That's what's going to be sent out as alerts. In addition to that measurement, we also have we also want to sort of collect any previous information we have from that spot on the sky that has shown some sort of change. And so we collect that information in what we call a DAA object. DAA here stands for difference image analysis. That's basically an aggregate of all the DAA sources that we might have observed at any given point in the sky. So if something is rising or falling, like that set of DAO sources over time will be aggregated into a DA object. And then I've said alert here. People talk about the alert stream a whole lot. What is an alert? It's basically just a way of us transmitting the information from this difference imaging process to the users in a timely way. So for each visit, for each DA source, we will make an alert packet, and that has whatever we know about the DA source, whatever we know about its aggregate, the DA object, and it also includes a postage stamp of the template image and the difference image. And all of this will then go out to a set of brokers who will be able to provide amplifying information or filtering information and make that available to users. I think we'll talk more about the brokers later. Um, we also store copies of this in databases, so you can, in addition to listening to the alert stream, if you want to instead query the database, just ask what was observed in this patch of sky at any given time. We'll also have that information available. So the goal with the prompt processing is really speed, and we want to make things available as soon as possible. But the goal of the data release production, the annual processing, is really to be comprehensive. So that's when we're trying to get our best understanding, the best information we have about any particular source in any particular image and make that available. So every production starts from the start of the survey. We're not processing each year separately. We're processing all the way from start. every time we do a data production. Um, we use this to build coads to give us additional depth. Um, because we have so many epochs, that lets us do very good rejection of artifacts and any sort of transient effects that might be present because we have lots of other epochs to compare to. So we can get a coad that really reflects just the static sky. Um, but we're not losing any of the time domain information because we're also um, using those static sky coads to then do image differencing again, much like we did in the prompt processing, but on every single image that we have taken that goes into this data release. So the data release itself will also contain like a consistent set of DAA sources and DAA objects over the entire survey. So just to highlight some of the products that are sort of most prominent in the DRP, sorry, in the data release. Um, we'll make those single visit and difference images available. The images themselves will be available. The coad images will be available. We um, we do measurements on coads. So that's what a lot of the static sky science cases are really focused on is getting measurements of galaxy shapes or star colors. Um, but then we'll also make all those DA sources and DA objects I talked about available. So that will let you identify anything that has changed more than 5 sigma from the template, like I mentioned. Um, and just to round out this set of data products, um, for all the objects we detect, so anytime we see something in the coad or any of these DA objects where we've detected one particular visit that where something has gone above 5 sigma, we'll also do force photometry on all the other visits at that position. So we're saying we know that there's something at this position because we saw it in the coad. We want to make a measurement holding that position fixed, but measuring the flux that's present at that position in every single visit. Um, so that's yet another handle on time domain information that doesn't rely on things necessarily having sort of clearly detectable transients, but might but gives you additional information. For example, if you're trying to measure, set upper limits on the flux from some source that you detected in one image but didn't detect in the others, we'll have force photometry that gives you those upper limits or below 5 sigma flux or whatever other time domain information you would need there. So that's just like the brief overview that I want everyone to have of the data products as we sort of go toward so that when you are able to get to the data products, you'll have some familiarity with what we're producing. And now I just kind of want to cover a little bit of status of the commissioning process. So I said that we're a functioning observatory that's on sky, and to go into more detail about what I mean there. Um, in the early phases of the project, we realized that because we're basically a single instrument facility, um, and we have both a complicated telescope and a complicated camera, it would be very challenging to do commissioning of these together when they're both already integrated, and that it would be much uh, easier for us to commission the telescope if we had sort of a smaller test camera that we could use to just test the observatory, the telescope, all the mechanical details that you need to make the observatory work well. We could test with the small test camera first, while the big 189 sensor LSSTCam was still in the lab undergoing its own sort of electro-optical testing. And so that's what we did. So we went on Sky with the commissioning camera, ComCam, on October 24th of last year. And we basically observed every night through December 12th. Um, this is basically nine sensors. They're the same science grade sensors from the batches of sensors that we use for LSSTCam. Um, and if you count out how big nine sensors is on the focal plane of LSSTCam, you see it's this red rectangle here. That's the size of LSSTCam's sense of focal plane relative to the full LSSTCam. And so that's what we were observing with for in this sort of 2.5 month period. And like I said, that was really focused on optical testing, making sure that we knew how to focus the telescope, could reliably focus the telescope under a variety of conditions, and could work on sort of things like image quality, um, all those sorts of commissioning details. This was just very successful. We managed to um, have uh, really, really great in focus images for most of this run. So because it was so this process was so successful at getting us good science grade imaging, we decided that we should use this time for collecting a science validation data set. And that allows us to have to not just commission the physical telescope itself, but to start to commission the pipelines using real data from LSST cam like sensors. Um, and this is giving all of us in data management uh, new challenges to work on to make sure that we can handle the full LSST cam data set when it becomes available. So we've sort of structured that science validation data set to be intentionally spanning a kind of variety of environments, a variety of processing challenges. Um, and because this is data that we're going to release, and I'll mention this more in a second, we want to make this useful to a broad set of users for assessing a broad variety of science cases. So this is including both high galactic latitude fields, sort of the standard well-known cosmological fields that are listed here, low galactic latitude fields, dense star fields, nebulous fields, things that are really going to sort of require us to push the envelope on our uh, pipelines. Um, and this was really taken to get depth rather than area. LSSTcam is really small compared to, sorry, ComCam is really small in area, so there wasn't a whole lot of reason to do a lot of tiling. And instead, we basically picked the small set of fields and really did lots of dithering on them, lots of epochs. And so when you look at this data, there'll be lots and lots of epochs and lots of time domain data. Um, like the sampling is much denser than the actual LSST survey will be because we were just sort of sitting on the same field so often. Um, I should say here that the reason why I'm not showing any pictures as much as I would love to show pictures is that the agencies have requested that we do not show that we want the public's first experience with Rubin data to be with the full LSST cam pictures that show the full sort of magnitude of the capabilities of the observatory. And so for this reason, we're not releasing the ComCam images until we've been able to get LSSTCam on Sky and been able to show that to the public and do the press releases and associated media events. So as soon as we can, we will make all of this available, but it all hinges on getting that LSSTCam data available to the public first. So we're aiming for this summer, and all of us hope that it can be as soon as possible. Um, so yeah, just to give you to move into a bit of the timeline from here looking forward. So ComCam observed in October, November, December, and then was taken off the telescope in order to be able to start doing all the mechanical work required to switch from one instrument to the other. There's lots of utilities and cooling that need equipment that needs to be changed over to support LSSTCam. So people are busy doing that right now. Our goal is to have LSSTCam installed sort of by March and be able to start pumping and cooling down. And then the goal is to go on sky with LSSTCam in April. And then from there, we'll go through the same sort of engineering test, image quality, that sort of work to get the observatory functioning well. And after that, we'll proceed to a similar set of science validation surveys with the camera, again, to make sure that the scientific performance is what we expect from the camera and to debug any issues that need to be solved there before we start what we call like the actual main 10-year survey. So this is just the detailed Gantt chart, just if anyone wants to refer to it in the slides when they're online. I don't think most of these are not important at this point, and I think I've highlighted the key ones that are relevant, but this is just for reference. Um, and so I'll basically end by talking about the release of the data. So we've said that there will be a series of data previews. Um, prior to the sort of full data releases, um, that will give people access to some of this commissioning data. So Data Preview 0 was simulated, that's already available. Data Preview 1 is going to be the ComCam data from this science validation survey that I was talking about. That's what we expect to be able to release this summer. We are working on it as we speak, in getting the data production running, and trying to really optimize our pipelines for the set of images to get the best data products out on that time scale. And then once we've done the science validation surveys with LSSTCam, we'll then go through a process of preparing those to release as data preview 2. And that will be the last preview release before we go into the sort of more normal mode of operations where we're releasing the data releases on an annual cadence. Um, and we know that people are also going to be interested in the alert stream. And our goal is to also be able to make some alerts available in a high latency, potentially high latency mode. There's a lot of technical challenges here with getting the alerts up and running, that I think we'll talk more about in the subsequent sessions. But it is our goal to make these available as soon as we can, because we know that this is something that people need to prepare the brokers and prepare their own tools to be able to make the most of these alerts. So we know this is all important to people, is getting those out as soon as we can. So we're definitely trying to do that as well. And so I think that's all I have to say here. So I'll just point out that there's a link to the For Scientists website, which has been recently updated and should have a really comprehensive set of resources if you want to know more about the observatory. And I'm happy to take any questions. Thanks.
Thanks so much, Colin. It's really exciting to see just how close down Rubin's science really is. Any questions? Yeah.
I was wondering how close you're working with the brokers in this early phase, ComCam. Is the broker process being validated already, or is that something that will happen in the summer?
We have not attempted to integrate the brokers with the ComCam data. So the ComCam data was our first chance to really run the prompt processing pipelines ourselves in a real mode. I meant to add that to the slide and I forgot to add that, but we were running the prompt processing pipelines during ComCam to get those fully functional. And so that was really our focus during ComCam, and it just ended up being too short for us to have to try and do more integration with downstream brokers. But we expect that'll be more of we'll do more of that during LSSTCam commissioning.
question. So it's not really microlensing related, but what sort of will there be moving object flags in the Rubin catalogue? So or will they be just separate but obviously correlated DIA objects that will the users will have to work out themselves?
Yeah, there's if I go into the full data model, you would see that there's a whole set of catalogs that are specific to solar system moving objects in addition to the DA objects. I've sort of elided a lot of that. But yeah, so we run moving object detection every night during the night on the difference image detections. Those go to the Minor Planet Center, and then they tell us, okay, these are part of a moving object, and so we annotate the catalogs with that information. So if the if the Minor Planet Center says this is a moving object, we'll know that. And then same thing with the data release, we do another comprehensive reprocessing. So we'll be searching for minor planets again in the data release and annotating detections that way as well.
So I saw the optics are quite complex in the Rubin. Is there any information on the optical alignment or image quality?
I don't have the image quality slides handy at the moment. There might have been some of those released at there's a AAS town hall recently. We're uh, yeah, I think our goal with ComCam was to sort of get the algorithms working to get the image qualities sort of sorry, what am I trying to say? Our goal with ComCam was to get the active optics algorithms like functional and able to focus the telescope. And then we've been using the time from ComCam on Sky in preparation for LSSTCam going on Sky soon to identify, okay, what are the most important things to improve in terms of image quality to deliver the images that we to meet our requirements and deliver the best images that we can when LSSTCam goes on Sky. So it's still sort of an area of active improvement, and I don't have the numbers off the top of my head.